I'm going to run through the Half-Life prac, which is modeling radioactive decay with dice. There's the method. If you want to pause this and have a quick look, the method is here. But I think the video pretty much explains everything, so we're just going to go straight for the video here. So this, we did it with 10-sided dice, and we did it with 6-sided dice. So I'm going to show you the 6-sided dice one first. So I'm just gonna run through the Half-Life prac, which is the dice, and we're gonna model dice decaying for the random nature and the random process of radioactive decay. So here's the prac. I'm going to stick pictures of this up anyway, but we've got two sets of dice. We've got a 6-sided dice and we've got 10-sided dice. We've got table of results and we've got just a blank area to roll the dice. So we're going to start off with 50 dice. You can see there in the table of results it's got 50. So it just needs Sir to roll these dice now and pick out. So you're going to choose a number now, sir.
So I'm going to choose number 1, just because 1s are easier to spot. Could it have been any number though, sir?
Yes, it could have.
Okay.
And we need to keep that number the same then throughout. So
2, 3, 4, 5, 6, 7, 8. So 8. So 8 decayed. And then I would take 8 from what? So my number remaining is now 42.
it's important now to leave those 8 dice out because they've decayed. So the biggest mistake now would be to put those back in and keep counting 50 dice every time. But now we've got 42 going back in to the tub. We're going to reshake them and model decay yet again.
Can I pick a different number now, sir? Or
No,
do I
would stick with 1. I would stick with 1 because that's what we've chosen.
2, 3, 4, 5, 6, 7, 8, 9.
9 that time.
Which gives me 33.
And rather than go through the whole thing, I'm just going to take pictures now of every one so we can look at those separately. So again, you're going to put those back in and we'll take photos now of each roll. And that's what I've done here. So you can see after 3 rolls, there was 5, and then that brought that down to 28, and so on and so on, until we got down to the last 4. And you can see my results here after 15 throws. They started. So this is a random process, and you can see that by the fact that on throw 7 there was 0 decayed, so they were 17 put back into the pot. But these can be graphed, so you can see from my 6-sided graph then we can get a decay curve going. You see a few anomalous results there. Throws on the bottom, number remaining on the side. I've got a nice little scale, and then I can also calculate my half-life. So if I start on 50 dice, 25 number remaining. So this would half every 3.8 throws. I get some sort of half-life. And you can half 25 again, which would be, I don't know, like 12.5, wouldn't it? So 12.5 would come here. And you can see that probably the difference is going to be around about 3 again. Maybe it's just over 4. But you can have the same sort of gaps between every half-life there. So the half-life of a 6-sided dice is 3.8-ish. So yeah, 3.6 actually, when I look at that scale, because 3 is here. So 3.2, 3.4, 3.6. Let's look at now the 12-sided dice, or the 10-sided dice, I should say, and see how that would differ. Okay, so exactly the same process now, only we've got 10-sided dice. So hopefully you will see the probability now decreasing, and you'll get less of a decay curve. So the decay curve, it'll take longer to decay. So hopefully that's what these results are going to show. So, now these are going to take a bit longer to pick out the number 1s.
I might go for zeros on this one, though, sir, because the zeros
they're easy to see.
Spot.
All
Yeah,
right.
I'm going to go for the zeros.
Okay, so as long as you
1,
keep consistent.
2, 3,
Any more zeros there?
4. 4.
4 zeros. And you can already... I just want to pause there a sec, because we chose number ones last time, but we chose zeros this time, and I always said keep them the same. We chose zeros because this was a fresh investigation, so I had no previous results, so we chose 0 from the outset. So I just wanted to make that clear there. See that there are less.
If we just compare then, so if we have our 6-sided dice, we had 8 at the start, and it's 4 this time. Okay, so
let's go for one more throw, and then we'll take the photos again. So obviously we're leaving those out, because that's the Decay. Shake, shake, shake.
2, 3.
I can see one. I can see an orange one.
4.
I can see a white one.
5.
Ooh.
6.
Oh, a fair few on that one.
Yeah.
Yeah.
And then that would leave us 40, and that's still, if you want to just compare the probability, we had 33 remaining F2, and we got 40.
Well, we'll see now with the photos. So let's have a look at the photos. What have I done by here? Oh, right, okay. So you can see after the third throw there, we only had 1. So we went down to 39. And then we got a full set of results here. So we had 19 remaining after 15 throws. So to get a full set of results there, would have had to kept going and going until we got down to about 3 or 4 dice remaining, the number remaining. But just didn't have time for that, and just wanted to draw up a quick graph then for a 10-sided dice. You can see immediately, compared to this fella, if we just put them side by side, that the decay curve is, should we call it shallower? It's a longer half-life, so if I zoom in on the half-life there, so when I come down from 50 dice to 25 dice, you can see it takes 10 throws to get your half-life. So the half-life is 10 throws there. And we couldn't extend that anymore because we haven't got enough data. Which brings us to, how could we extend this investigation? Well, really, you can see all those anomalous results there. These anomalies, to reduce the number of anomalies, you would take a mean. You take an average of many, many sets of results. And the way to do that, in this case, would be if I got a class of students doing the same thing, and then we would collate our results, which if we go back to our original, the specified practical sheet, it shows that. So it shows you a typical table with your number of decayed dice and your number remaining. But then it also suggests that you may want to collate your groups. So your group 1s, group 2s, and then, by taking an average, then you reduce... No, sorry, I shouldn't say average anymore. By taking your mean, you reduce the number of anomalies. And that's pretty much it on this paper. That is the prac that models radioactive decay.